Okay, in this video I want to reiterate the importance of what we call the five-step process for solving a problem using Newton's laws. First and foremost, number one, the free body diagram. There's a couple of things that we need to make sure that we get right on this, because if we mess up the free body diagram, it will literally have ramifications all throughout the problem. So first and foremost, for the free body diagram, you need to draw a free body diagram per object in motion. So if one thing is moving, you need one free body diagram. If two things are moving, two free body diagrams, etc., etc. You need to draw all the forces acting on that body. Next, you need to have all the directions. Of those forces. This is very important because if we get any one of these steps wrong, it's going to carry over and really haunt us for the rest of the problem. I cannot stress how important. Previously, in previous chapters, we drew sketches of problems to help us and to kind of guide us through the problem. Now we're at that stage of the game that we warned about in the beginning of the semester, where the sketch itself becomes part of the problem. And so we have to make sure that we get that right. Number two, what I want us to keep in mind about number two is that it's an autopilot step. We're going to do this no matter how simple or how complicated the problem, because it's going to guide us. And we're just always going to write down the sum of the forces in the x is the mass times the acceleration in the x, and the sum of the forces in the y is equal to mass times the acceleration in y. And we're going to do this once again for as many bodies as needed. So what this means is that we can find ourselves in a situation where perhaps the notation becomes a little bit awkward. You know, what if we have a situation where we have two masses hanging over a pulley, right? We have mass 1 and mass 2. Well, how would we write out Newton's laws for this scenario? Well, we would have the sum of the forces in the x direction on body 1 is equal to mass 1 times the acceleration in the x direction of body 1. Sum of the forces in the y direction on 1, mass 1, ay1. And we'd have to have the same type of thing for number 2. It means that the notation can get a little bit hairy, but once again, it's an autopilot step that assures that if we did our free body diagram right, we have everything accounted for. Okay? Step 3 is fairly self-explanatory. We take what we learned from the free body diagram and drop it into the left-hand side of these. Again, what is the left-hand side? The left-hand side is this side here. And when I say replace the left-hand side with any of the forces on the free body diagram, we once again have to remember that we establish that anything going to the right is positive, anything going up is positive, anything to the left is negative, and anything down is negative. That is our typical convention for an x and y coordinate system. We will find ourselves in situations where we might want to tilt the x and y coordinate system, but we will always use relative right, relative up as positive, relative left, relative down as negative. Okay, let me talk about step 4, which is probably the weirdest one to wrap our heads around. So step 4, where we say apply any extra physics. This is where we would want to apply any force equations. What do I mean by a force equation? Well, we've seen one of them already, right? That the force of gravity is the same as the mass of the body multiplied by the acceleration due to gravity, right? That is a force, right? Mass times an acceleration. It's how much gravity is pulling you down. So typically when we draw in the free body diagram, we just call it F sub g, but we can always plug that in later on. Other things that will come up is things like a frictional force has a certain formula which we haven't gotten to yet, but this would be the time to plug in the actual formula, would be when we apply any extra physics. This is also where we would apply any sort of assumptions, like for example, a standard one is that when you have an object on the floor and you're pulling it, that object never jumps off the floor typically, nor does it tunnel through the floor. That would just be kind of strange. So typically in those situations when something is locked to the floor, the acceleration in the y turns to be 0. Another example of this would be if you have something hanging, right, by some rope, right, and let's say it's being pulled in some other direction, right. For this body here, well, no matter what this rope does, if it's hanging over a pulley or something, it's probably never going anywhere left or right. So for that, that's where we would make the assumption something like the acceleration in the x is 0. Step 4 is the wonky one, but it's the one that we really have to think about and apply all the stuff that we learned from previous chapters. Lastly, step 5 is just algebra. That's when we solve for what we actually want in the problem. So that's the piece that, that if you get through steps 1 through 4, all the physics is done, and at that point, you're just living in math land. What I will say is that what can this 5-step process do? Right? Number 1, as of right now, it is the only process that has force in an equation. So if we hear the words force, we're going to think 5-step process. Even if the force is the unknown, none of our kinematics equations are going to tell us what the force actually is. The only way to do it that we know of at this point is through the 5-step process. What are the quantities that the 5-step process can tell us? The quantities it can tell us are values for forces, values for masses, and values for accelerations. So, if you think about it, to this point, the 5-step process is the only way that we can get forces and masses. Accelerations, yes, you can get them through kinematics, but a lot of times we want to get the acceleration from a force and a mass. So typically the accelerations tend to be the outcome of the 5-step process and then is used in kinematics. Obviously, there's not a one-size-fits-all to that, but it's at least a good enough go-to for about 85% of the problems that we will solve. So this really is the most important piece that we need to know from this chapter, because as problems start getting more and more complicated with more and more forces, things like the free body diagram is going to become important, and the autopilot step, which might seem redundant, and it might seem like I'm trying to make you do something just to do it. Trust me, there's a good rhyme and reason to this, and that will become very clear when problems get more complicated. Until then, if there's any questions, comments, complaints, or concerns, please do not hesitate to ask. And until next time, never stop thinking.